Hi everyone. Thanks for coming. I am a math PhD student who was studying this QED thing for past 1 month or so. Hello. So that's why my presentation won't be admittedly so perfect, but I'll be presenting whatever I can understand, and it'll start from so let's see. It goes in these 5 steps I wrote here. By the way, this node is available on the Discord server, in the channel, seminar channel, for whoever wants to see it along my talk. So it'll start from a classical theory and go all the way, say, to the applications, although I'll be skipping a lot of things. So quantum electrodynamics is a quantum field theory that describes the interaction of charge matter and electromagnetism. And there's special relativity by design, Lorentz invariance. So it passed a lot of experimental tests, for example, passing a experiment of this accuracy. So we'll be focusing on the spin half fermions, such as electrons. And the 5 steps that I'll be going through in order, in this talk, it will be just first to describe the relativistic theory of electromagnetic field, relativistic theory of fermion field using the Dirac equation, and the Lagrangian for QED, and how to change these, upgrade these things into a field theory with the correct commutation relations, and I'll describe the Feynman diagram rules briefly as well, and talk about what Compton scattering is, and anomalous dipole moment of an electron. So I actually ended up talking about this thing to several people, but I mean the schedule of the presentation itself, but it is a technical presentation because it assumes a basic understanding of the quantum field theory for scalar fields. So all the associated formalisms will be kind of taken as granted, so to speak, although I'll somewhat be repeating them perhaps. Okay, briefly let's cover the notation used here. So this is a Kronecker delta symbol, which picks up whenever 2 numbers are the same, 1, otherwise 0. And we'll be using the metric signature of plus and if otherwise, mostly negative sign. Yeah, like this. And Einstein's summation convention, as per usual for tensorial stuff. So up index and down index, mu here will pick up a summation here in the summation. And we'll just write a square, for up down sort of thing. This means inner product in mathematical language. This may look unfortunate because it may look like a mixing of notation, but it'll be pretty much clear. So it's also important that 3-dimensional quantities will be written with a boldface. And yeah, so this is a vector, 3-dimensional vector, and this will be a 4-dimensional vector. Oh, by the way, is my screen clean and everyone is following and so on? Is it all right?
Yes.
Okay. So I'll be also using the natural units, where I'll be assuming that a lot of these constants are just 1, in terms of choosing the right units. And this notation will mean defining something. So fx and then x squared plus 1 is defining a function. And this is the relativistic energy of a particle with 3 momentum p. And we'll be using this kind of notation often, 3-dimensional integral of a 4 momentum p. And that's done for this particular implicit notation, where this EP is a this particular mass dot. So this is called mass shell condition because it looks like a hyperboloid. Anyone who is listening should, I guess, already know. But yeah. Okay, so the first part, max electromagnetism with tensors. I'll be going over this pretty briefly because apparently people already kind of know this. So this is a non-relativistic classical Maxwell's equation in its full glory. where like J here is like the charge current, and like E and B are like electric field and magnetic field. This is time derivative. And the Lorentz invariance formulation of the vacuum Maxwell's equation, where the charge current is 0, is given using vector potential A mu, where like this. That's the equation. We'll provide a simpler form later. But the way to, so to speak, derive A from E and B is to like use how like B has like 0 gradient and like do this thing. But like the more correct way to formulate it is to start with A and then like and then give rise to E and B, because A is the quantity that changes like Lorentz covariantly. In this formulation, the vacuum Maxwell's equations are equivalent to. So this gives 2 of the equations, and the other 2 are just baked into the definition. So that's Maxwell's equation. But like another way to formulate this is to use the Faraday tensor, written like this. And if we use this definition again, then we'll be arriving at this kind of like pretty matrix, where you can see this sort of division: E, 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 B, 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 and it's like all anti-symmetric. So if you flip it, like it picks up a negative sign. Okay, so it's also possible to reformulate vacuum Maxwell equations in this form. I have to. Oh, this is my friend. I can formulate vacuum Maxwell's equation like this as well. So this is also vacuum Maxwell's equation. 2 of them. Other 2 is just like built in. And this is using the Lagrangian. Oh, yeah. Looks like I haven't mentioned it like beforehand. Like looks like the order is a little mixed up. But this is the electromagnetic Lagrangian density that can be formulated using the Faraday tensor, where like this expression is like the strength of F. It's like the Frobenius norm of a matrix, and that's Maxwell in terms of F. So with sources, we can get this using this Lagrangian.
Hey, sorry, can I interrupt for a little bit?
Yeah.
Yeah, so I want you to just understand what the Lagrangians actually is in terms of the physical fields E and B, right? Do you know what they are?
You mean E and B?
Yeah.
Yeah, electric and magnetic field.
In terms of in the Lagrangian, right? You're writing down Lagrangian as trace F squared.
Oh yeah, here. Yeah.
Yeah. So what is that in terms of E and B? Do you know?
No. I guess I could write it down.
Yeah, it's E squared minus B squared.
Oh, okay, that's very nice.
Yeah. Mm-hmm. So those are the 2 covariantly invariant terms that you can write down with the
Right.
E and B, aside from E squared plus B, which is the energy, right? So you see they play this canonically conjugate coordinates in this EMM field theory. But yeah, that's something important that you might want to keep in mind, because, where did you get this, right? Why are you writing down trace of F squared? Right?
Yeah, that's fair. I'm sorry, but like like the Google Meet has like 1 hour limit, so I'll be kind of like trying to rush through this thing. I think like we can talk about like comments like at the end. Like I'd normally be like open to this sort of interactive thing, and like I kind of said that I would be open to it, like especially.
Yeah, go on.
Yeah, like I need to finish this. Okay, I will go on. Here we go. So the most natural framework encapsulating these. We can like reformulate this, like all this using like a bundle language, but like that's kind of like not exactly what we're looking for right now. We'll be ignoring that connection, bundle, and curvature. But it's like a really elegant mathematical formulation. And now here's a gauge fixing. So we noticed that like changing the A mu by adding this gradient of a scalar function like will not change the Faraday tensor at all. Because of that, like this change actually doesn't like affect the theory at all. Like this is called a gauge transformation, and imposing conditions so that like no room for such freedom is allowed is called gauge fixing. So like we're trying to like disallow any redundant flapping of a theory. So there are two like important like common steps used for gauge fixing in electromagnetism: Lorentz and then Coulomb gauge. Lorentz gauge is where like we assert that the divergence, for divergence of the vector potential is 0, and the Coulomb gauge is like that plus saying that the three divergence of like the vector potential, the three-dimensional part of the vector potential is 0. And the thing is like this expression is Lorentz invariant. But this one is not, because it'll just like change with a frame of reference of in your space-time. But it'll still be like reducing all of the degrees of freedom to just 2, which is like the physical degree of freedom for electromagnetism. And it'll imply like these two will imply that like A0 is 0 by literally just subtracting from one to another. That's what you get. I think I forgot this or something. Yeah, but like it doesn't matter. Like if you said like it as 0 like everywhere, it's the same thing. Okay. So we'll move on to the Dirac equation. I think I'll spend quite a bit here because so the Dirac equation will be really important to understanding it like thoroughly will be important to like coming up with a correct quantum field theory for like the fermions. So it's a relativistic formulation of the Schrödinger equation. And historically, although like not very intrinsically, it was derived by Dirac like trying to like change the Klein-Gordon equation into a first order form in time, where this one like is trying to work with relativistic energy, and like it has double order time derivative, and Dirac tried to change it by a formal factorization as such, like this, if such an expression exists at all, that is. So like assuming that it exists, like we can just like say that like psi vanishes under this operator if and only if, well, it vanishes under, okay, not if and only if, but like it vanishes under this is kind of enough to say that like it vanished under this. The black is too strong. So this will be the Dirac equation essentially. But how do we realize this formal square root? This formal square root. It is realized by considering a wave function psi valued in C4. I have to like turn off the notification. Hold on. Okay. Can everyone still hear me?
Yep.
Yeah. Okay. Cool. I turned off Discord, so I was like, it doesn't affect, but okay. The formal square root can be realized by instead considering a wave function valued in C4 and introducing the Pauli matrix and Dirac matrices. They are somewhat cumbersome to remember precisely, but it's a matter of partly a practice, I guess. So like this one is like diagonal, anti-diagonal, anti-diagonal, and diagonal again. And the Dirac matrix is like you get the sigma on the two slots, and you invert the sign for the indices mu equals 1, 2, 3, and don't invert it for mu equals 0. Note that like this sigma 0 is precisely the identity matrix in 2x2 identity matrix. And they satisfy the anti-commutation relations, where like, just remind you, anti-commutator is just AB plus VA. So you do like these two, and you get Dirac, Kronecker delta, and then for the gamma matrices you get the Minkowski metric signature. I2 and I4 are identity matrices. So that's how we get from this thing to, I mean, this is all definition, and then like this is the non-trivial part, this part. Because like that's where like this relation gets used, right? So we do get the formal square root after all. So the slash here is a Feynman slash notation where we're doing like a contraction with a of a gamma matrix with like another tensorial quantity, like a labeled quantity like this, and using this formalism and multiplying by negative I from here, we get this. That's what people usually call the Dirac equation. And there are like several different ways to rewrite it. And one way is to separate out the time derivative and multiply by a gamma matrix, so that you get this formulation where this Hamiltonian-like quantity is given by this. And the Dirac equation can also be reformulated as an equation of motion for the Lagrangian given by this. And where this bar is, you take the conjugate transpose and then multiply by gamma 0. That's what the psi bar is. And these are the associated canonical momentum. Yeah, so it describes how a fermion of like spin half moves evolves, how its quantum mechanical wave function evolves. The way that the gamma matrices and the spins are like intertwined is a little bit more to explain, but like I will not explain it here. Okay. So in order to understand like how to solve a Dirac equation, we'll be describing like several different concepts on the way: chirality, antiparticle, and spin. So we'll be getting a general solution, and using that, like you will be quantizing a fermion field. By quantizing, which we mean like upgrading the fields to field operators. So chirality. That's what we do here is to replace the four-dimensional Dirac spinner, four-dimensional Dirac spinner into two-dimensional Weyl spinners like this. So why do we do this? That's because the Dirac matrices are just like naturally divided into like 2 by 2 like this block matrices. So that's how you arrive at these two. You might like the above Dirac matrix, Dirac equation just reduces to this like completely, where this p hat are like the momentum operators, and the bold sigma is a like so-called spatial like I guess spin matrices. So you can also alternatively write this like this, with a bar making the sign split on the spatial part more clean. So due to the sign difference tacked to sigma times p, like there's a difference between this and this. So like that's why we call this like left-handed and right-handed, although I am yet to fully understand like precisely why it's like, you know, left-handed or right-handed, but it's very clear that they're different. And like the distinction is called chirality of a Weyl spinner. We can also, since you notice that like it's you act by an operator on this psi r, and then you get psi l, and then psi l, and you get psi r again. So it's like left, right, they change around. So you can like compose one thing on top of itself to get like you act on L to get like this to get L again, something that looks like an eigenvalue equation. Anyway, so suppose that like now we talk about antiparticles. So suppose that besides a momentum eigenspinner they're diagonalized by like P0 and P. I forgot to put the hat here. The Dirac equation for psi gives the following, where we take the above one equation and like replace it by just like plain numbers. And you actually get like this equation where P squared is equal to M squared. And then like if you try to solve for P0, you'll get like plus or minus. And people got like quite annoyed by this because they didn't want negative energy. So like there wasn't like an alternative interpretation for this in seeing the negative energy, like ignoring the negative energy solution, so to speak, and just thinking of like the negative frequency solution. Although I may be saying things pretty wrong here. I don't understand the full like physical history of this. Maybe we can discuss afterwards. But anyway, we can do a direct substitution and see that like these two are solutions to the Dirac equation, where we have this four-dimensional spinner and these four Weyl spinners, and then there's like this phase factor thing, where like the first one represents a like forward moving wave, and this one represents a backward moving wave. So it can be just brute force like checked as a solution, but both of them have like a positive P0. Yeah. So I'm just explaining these like formalisms, but like it'll just all come around to be very useful after all. So in the above solution where we describe like a particle versus antiparticle, we can further study it by asserting that these expressions are like the general forms of the solution for the UP and VP, where we're doing this square root of P dot sigma, and this thing inside is a 2x2 matrix, and it works because it works. It's a skew symmetric matrix, but like we can take a square root. There are only 2 degrees of freedom left for you in isolating this psi out. Now it's xi, isolating this xi out. And they turn out to be precisely about spin values, plus half and negative half. And a standard choice of basis for this psi. Sorry for mixing up psi and xi. I actually still don't know what's the right way to say them, but okay. The standard choice of basis for psi s and eta s is to write the first one as 1 0 0 1 1 1 1 1. So they're kind of like flipped upside down. But in any case, they're like precisely the plus half and negative half eigenstates for the spin operator. So like they will correspond like in experimental settings with the spin operator. And I believe the magnetic dipole moment sort of observations in the labs. Right, so S here represents the spin indices. Here, there's a spin index. So we'll try to discuss like how this leads to orthogonality relation, and then also a mode expansion of or a general solution of a Dirac equation. So it can be proven with some algebra that these two relations hold. So U dagger and you multiply them too, and you get this constant times psi dagger and psi. Same for V and eta. So this is not Lorentz invariant because of this EP factor. As I have said before, this is not Lorentz invariant. So we can kind of like hide that using this expression instead, U bar, where you multiply the gamma 0. And these are the Lorentz invariant expressions. It seems to be that this bar is like the correct way of seeing a conjugate of a U. So if we use the standard basis for C and the eta as seen above, then this inner product thing precisely turns out to be the Kronecker delta. So this is an orthogonality relation for the U and the V, because it's like one over 0 here. I mean, multiplied by 2m, that is. So using this relation, apparently, we can perform a Fourier expansion for general particle and antiparticle wave functions. So these are like the Fourier things as usual. This is like a, it's tacked on to this D3P as like a Lorentz invariant measure in the mesh shell. And this is like the amplitude, and this is the solution described above as like a typical particle solution. So it's like a linear combination of these things summed over two different spin states, and with like these different amplitudes. And the same kind of same kind of formalism holds for antiparticles with this amplitude and this spinner. And you sum them up to get like a general solution to the Dirac equation. So, right. What we'll be doing later is to substitute these A and B by quantum mechanical, creation and annihilation operators. Right. So we see that like talking about these like Dirac formalisms like relating to how to solve the Dirac equation has like led us to introducing the chirality spin and the antiparticles allowed us to reach for a general solution of the Dirac equation, and it'll be used for quantization later. So now I'll talk about like the coupling of Lagrangian and the coupling of the charge matter and the electromagnetism in the quantum QED Lagrangian. So the fundamental like tenet of classical field theory is the action principle, where like we try to find an associated quantity of like Lagrangian density, and then like perform this in like try to find a saddle point, so to speak, and that turned out to be equivalent to the Euler-Lagrange equation. So finding this sort of quantity is like also very meaningful in the case of quantum electrodynamics as well. And naively, we will think that like we'll just want to combine like the Dirac and like electromagnetic Lagrangians. We actually did talk about it briefly above. And like when like there's no charge matter around it, like this is like the correct Dirac Lagrangian, but there is no interaction term between these two. They're kind of like playing around separately, and the introduction of such can be done by asserting that like there's a U1 gauge symmetry for the QED Lagrangian, and what this means is that like when we perform the substitution transformation of like replacing a psi by psi times a phase factor that can depend on the point, we also want to assert that these like changes happen to like a modified derivative called the gauge covariant derivative d mu, which goes from like this more ordinary partial derivative plus this so-called gauge field with a coupling strength q, and like we assert that this gauge field transforms by this way as well. And when we assert this, we actually do get a satisfactory theory of electromagnetism. So the Q here is like the coupling strength, and for electrons, that'll be the electron's charge. So here's some math to work out that this actually does work out, like does leave the Lagrangian invariant. Let's see. Right. So like that's how we arrive at the final QED Lagrangian, where we replaced initially it was this slash of like the partial derivative, and then it became big d-slashed. Okay. So we'll now move to the procedure of replacing the field quantities by operators. So we'll discuss electromagnetism and like the fermion field separately. So you know, this is like trying to mimic the pre-field quantum mechanical like commutation relation between position and momentum, and seeing that as like a fundamental aspect of the quantum theory, and supplanting that into like a development of a quantum field theory. So asserting that, and then like performing a mode expansion, and then like seeing if like the creation and annihilation operators also respect the commutation relation is kind of the point. So the equal time commutation relation for the electromagnetism is a little different, where the usual delta is replaced by the transverse delta. So we're taking this of like the field and the associated conjugate momentum, and it computes to be like the electric field, and we assert that is the transverse delta function, which is defined in this way, where you have this extra factor here. And what it does is it projects a vector to the transverse direction of P. So if this is P, and like this was the normal plane, then it kind of like projects a vector to like this plane. Although this plane is, you know, is the normal in the four-dimensional sense. I actually don't fully understand the way that this works as an integral operator, which I'll be maybe discussing later. So replacing the usual delta function by the transverse delta function assures that like this thing like correctly vanishes in the Coulomb gauge, because otherwise like it becomes a non-zero thing if we just use a normal usual delta function. And it also computes the creation and annihilation operators to have the correct like commutation relation, which is where I'm skipping a little ahead because this should go down below. The mode expansion works by expanding the field operator in terms of, well, this is the usual Fourier kind of thing, and then we have these two things from that we kind of see from like the scalar field theory, annihilation and creation operators, forward and backward moving waves, and here are the polarization vectors for electromagnetism, which becomes, you know, that there are only two of them because when you look at like forward moving wave, and like I actually don't fully understand this actually, but it's like when you have a three-dimensional vector and like you're only looking at like the transverse component, and that's just 2 degrees of freedom. It's kind of the idea of like why do we have these two polarization vectors, and they satisfy these orthogonality relations where it's orthogonal to the direction of propagation, like they two are orthogonal to each other. And this is the Hamiltonian expression that gets derived if you use the correct calculations coming from above. And the fermions. The desired equal time anti-commutation relations are as follows. So you have a fermion field operator where A and B are the spinor indices. So it's 0, 1, 2, 3. Or I mean 1, 2, 3, 4 maybe. But so you have Tx, Ty, the T are the same, and then you have the delta function that picks up the difference of spatial coordinates, and then there's another delta function, a delta symbol for matching spinor indices. So we use anti-commutators, not commutators, because we're dealing with fermions, which respects Pauli exclusion. And a field quantization replaces fermion fields by a quantum field, and replaces the Fourier amplitudes seen earlier, which were like A and B, and then they become hat. They were amplitudes, now they are operators. So usual Fourier thing, with Lorentz invariant measure. And then there's a spinors that we studied from earlier corresponding to the two spin states. And then here are the two operators and the two plane waves. Working out like the commutators from these. Who joined? Someone joined. Working out the commutator for these, anti-commutator for these give you these delta function, spatial. And the associated normal ordered Hamiltonian is this. So I'll discuss like the Feynman diagrams rules briefly. Like so I mean, this is where like we kind of go back to the physical world a bit, where we can get like predictions of physical quantities by computing scattering amplitudes, and that comes from adding a lot of infinitely many Feynman diagrams, and adding enough of the lower order stuff is seen to be enough as application sometimes. Also, it's really hard to compute the higher dimensional ones. So we omit the derivation of the Feynman diagram. Well, partly I do not know how to do them yet, but here are the rules. So it'll be like a 3-vertex thing. The diagrams will have like vertices with like 3 ends, like this. And for every vertex that appears, you tack on this constant and a gamma matrix. Every photon line, internal photon line that appears, you do this Minkowski raising lowering, and this quantity p squared plus I epsilon. And for a fermion propagator, do this. Well, it's also kind of like easier to remember these if you kind of try to separate out the imaginary factors coming into these things, because otherwise the quantities that come into these are relatively simple. So additionally, we'll be using the polarization term for the incoming and outgoing photons, photon legs. And for Coulomb gauge, we do epsilon 0 is 0, and epsilon is perpendicular to the p. Each incoming and outgoing fermion or antifermion gets the spinor term u or v. And adjacent elements get contracted as tensors. What this means is these two things get contracted. Like if they were like nearby, the mu will be the same thing. And we have to ensure the conservation of momentum per vertex, and each loop picks up an integral. Here are some examples that I show, but without like the higher order diagrams, which often diverge and like need a systematic way of making them finite, which I am yet to learn. So here's an example of an electron-electron scattering. It's the symbols are small. So here's the incoming end, here's the outgoing end. So we're doing 2 electrons coming in and 2 electrons going out with the specified momentum and spin. And here are the 2 possible like lowest order Feynman diagrams that can appear. And you know, there's a first thing and there's a second thing where we computed like 1 for each. And you know, let's examine like what's going on here briefly. So we have 2 vertices. For that, we have like negative I factor like squared, and the 1 internal photon line, which gives another negative I. And each vertices give like charge squared. So that's the constant term here. And what's this? That's we do the terms that we have to do are like these incoming and outgoing legs have the spinor terms u, and we're doing like electrons and not positrons, so like it's U and not V. And there are two of these vertices that is represented by these gamma matrices. And you also notice that the tensor indices are mu up and mu down, and that's because of the phone line in the between, which it's technically something like mu and then gamma nu, and that becomes gamma mu, gamma mu. So that's the reason for these two things having the same tensor indices. They look kind of weird here, but like it's all just because, you know, like a lot of ugly indices here. They're just like these momentum and spins. And you also notice this thing, which comes from the photon propagator, the photon thing in the middle. And you repeat the same thing for the other one here, and you get this. By the way, it's P prime minus P because of the momentum conservation. So you repeat the same thing for electron-electron scattering to like electron-positron scattering and so on. So that's E minus E plus to E minus E plus. This is E minus E plus to 2 gammas. Gammas are photons here. So you get like an electron and positron, and they annihilate into light, as you know, as it's said in like the science fictions, although it's actually really happening. So this one is for electron positron. The lines here with the arrows are for the whether it's an electron or positron, because positrons are antiparticles, and like they are somewhat interpreted as like moving backward through time, although apparently it's not entirely meaningful to like see that as like a very meaningful interpretation of what an antiparticle is. Depends apparently. Here's also Compton scattering, where you're doing like light bouncing off electron. This is your electron, and light's coming in and going out. That's what's happening with these things. And this time you get weirder expression because of the internal fermion line. But yeah, it's the same thing. Oh, and by the way, like these things pick up the